Hello everyone, welcome to IIT Gate classes. So today we are going to start foundation course on TOC. Okay, so this will be a basic course and duration of this course will be 20 hours. Okay, so within 20 hours I will complete this subject and I will cover basics of this subject. Okay, so let us start this subject. TOC is theory of computation. Okay, so what exactly is computation? The first question which will come to our mind is what exactly is computation? See, roughly I can say whatever a computer do is computation. Okay, so what exactly computer do? We give some input and after processing, computer gave us some output. Okay, so in simple wording, I can say converting input to output is computation. Okay, so roughly I have written this thing. See, whatever a computer do is computation, like searching, sorting, calculations, etc. So more precisely we can say computation means converting input to output. Okay, now what theory means? Okay, what is the basic meaning of theory? Theory is how a machine perform a computation. Okay, so given a machine, how this machine perform computation, that is the basic meaning of theory here. Okay, so hence the subject is theory of computation. So machines here, we will study lots and lots of machines in this subject. So example of machine can be say finite automata. Okay, so machine example can be finite automata, push down automata, Turing machines, and so on. Okay, so we will study many machines in this subject. And given a machine like given finite automata, how exactly it is doing computation, we will study these things in this subject. Okay, how exactly this machine is doing computation, we will study all these things in this subject. So now read the full form again. Theory of computation. So now I think you all are comfortable. Theory means how machine perform computation, and computation means whatever a computer do is computation. That means converting input to output. So computer can do various tasks. So all the tasks which can be done by computer is nothing but computation only. Okay, and more precisely, if you want a little bit mathematical term, then I can say computation means given x, you want to find f of x. So you have a x, given x, you want to find f of x. Okay, so that is the basic meaning of computation. That means compute a function. That means find the value of fx given x. Okay, so you may think that obviously all the functions can be computed, like we give x and we find f of x. Obviously we can do for any function like this, but no, we cannot compute every function. Okay, or we cannot find f of x given x for each and every function in this universe. Okay, so forget about each and every function in this universe, just concentrate on this thing. Say we have a function from natural numbers to set 0 1. Okay, to set 0 1. Now I can say that there are lots and lots of functions from natural number to the set 0 1 which are not computable. Okay, so don't worry if you are not getting all these things. Don't worry, we will study all these things in pretty much detail in this subject. Okay, so you do not worry about all these things. I just want to say that natural numbers, a function from natural number to a set 0 1, there are lots of functions from this from natural number to 0 1. And how many functions are there? 2 power n. Okay, and n natural number set is infinite. So 2 power n are the total number of functions from natural number set to 0 1. Why 2 power n? Because each and every number, see, each and every natural number has two possibilities, that is 0 or 1. Okay, so each and every number has two possibilities. So 2 multiplied by 2 multiplied by 2 and so on up to n times. So that is nothing but 2 power n. So there are 2 power n functions, okay, from natural number to 0 1. And when we will go deeper into this subject, I will show you that this set, if you know then it's fine, but I will show you when we dive deep into this subject, the 2 power n is uncountably infinite. Okay, so in rough sense I can say like this. See, the total machines in this world, or you can say computable functions, are like this, but total number of functions from natural number to 0 to 1, these are like this. Okay, so there is no one-to-one correspondence between the computable functions and total number of functions possible, or you can say all functions. Okay, so here AF mean all function and CF mean computable function. So computable functions are very less, but all functions are very you can say very large in number. Okay, and if you want to visualize, then I can say like this also. See, this is a sea. Okay, sea filled with water. This is a sea filled with water. Okay, and you just take out one bucket of water from that sea. Okay, let me use different color, you will understand it much better way. You just take one bucket of water from this sea. The bucket of water which you have taken out is the computable functions, and rest all are uncomputable functions. Okay, don't worry, we will prove all these things in pretty much detail in this subject. You don't need not worry about all these things. I am just giving you introduction that why we are studying this subject. Okay, so basic aim of this subject is to prove that there are lots and lots of functions which cannot be computed, or there are lots and lots of problems which are undecidable. That is, problem is undecidable if we are not able to write algorithm to solve it. That means these cannot be solved. Okay, so imagine like this, C is we have entire sea of problems, and only bucket of problems are decidable, rest all are undecidable. Okay, so we will study all these things in this subject, and we will formally prove all these things also. Okay, so don't worry, this is a basic course, so we won't prove, we won't go into deep mathematics. We will give you just intuition, like we will give intuitive proof of all these things, that there are some functions which are not computable, and there are very few functions which can be computed, and so on. Okay, so this entire subject will be based on mathematics only, and we will try to find functions and so on. Okay, and functions with the help of machines we want to solve, or you can say we want to compute these functions with the help of machines, like finite automata, push down automata, Turing machines, and so on. Okay, so let's move to next slide. Okay, so in this subject, as I have told you, we will study two things, that is how machine perform computation. First thing is how a machine perform computation, like given FA, how this FA will convert some input to output. We will give some input and we will receive some output from this FA. Now, how this input is converted to output, that means how this machine perform computation. That this is the first thing which we are going to study. And in FA, I want to tell you something about this machine in advance, that output will be yes or no only. Okay, so here output will be yes or no, and given input, and given input will be string. Don't worry about all these things, we will study this thing in pretty much detail in subsequent slides only. So input will be a string and output will be yes or no. Okay, so how we are giving how a given string, how a string is given to FA, and how this is output is given by FA, that yes or no, and so on. All these things we will study. Okay, so how machine perform computation, this is the first thing which we are going to study in this subject. And second thing is computational capability of machine. This is very important thing. Okay, make some star on this thing. This is very important thing, computational capability of machine. This means that, see, given a machine, okay, given a machine and a task, okay, given a machine and a task, whether this machine is capable of performing this task or not, that is the basic meaning of computational capability of machine. Okay, see the wording, computational capability. Capability means whether this machine is capable of doing this task or not. Okay, so this is the basic meaning, and we will study all these things in pretty much detail in this subject. Okay, so computational capability of machine, I think this will be the last chapter in TOC, in which we will study decidable problem, undecidable problem, and so on. Okay, so all these things, decidable, undecidable, countable, uncountable, and so on, all these things will be covered in this topic, that is computational capability of machines. Okay, so I hope I have cleared all these things. So let's move to next slide. Okay, so course overview, we will have 4 chapters in this subject. The very first is basic terms used in TOC. Okay, so we will study, see, I have used the word string now. See, in the previous slide I have used the word string. Okay, so string, language, and so on. We will study few basic terms which will be used frequently in this subject. Okay, so that will be your first chapter, and this is the basic chapter. I think we will complete this subject, this chapter in this lecture only. Okay, so this is very small chapter, we will complete in this lecture only. Okay, next is finite automata and regular languages. This is the second chapter, and you can say this is the most important chapter in this subject. Okay, if you are comfortable in this chapter, that means you know more than 50% of the TOC. Okay, more than 50% of the TOC will be covered in the second chapter only. Okay, next chapter is your PDA and CFX. Okay, so this chapter is pretty much small. Okay, not very small, but it will be a bit smaller chapter, and we will cover this topic in a faster pace. Okay, fourth chapter. Okay, fourth chapter will be your Turing machines and decidability. This is again a very important chapter. Okay, so make some stars on this chapter also. So the most important chapter is finite automata and regular languages. Next important is Turing machines and decidability, and the third you can say third important chapter is PD and CFS. Okay, so the first chapter, or the basic terms used in TOC, where you will see very few questions from this topic, but we have to study this topic just because this will be the basic fundamental of this subject. Okay, so if you are comfortable with all the terms which we are using frequently in TOC, then I think most of the things will become easier for you. Okay, otherwise this subject will be very tough for you if you do not understand this topic pretty well. Okay, so let's start this first chapter, that is basic terms used in TOC. Okay, so the very first and the very basic term is symbol. Symbol is nothing but any character. Okay, any character is symbol. Like you can say A, B, C dot 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 Z. Okay, A, B, C, D up to Z, or small a, small b, small c up to Z, or dollar, or at the rate, dollar, hash. You can take any symbol, whatever you want. Okay, any character, whatever you want, that is a symbol. I hope I have cleared this thing. So this is very simple basic term, symbol. Okay, next one, and you can say this is the basic building block of this subject. This is the basic building block of this subject. Building block of this subject. Okay, so entire subject, you can say entire subject is based on symbols only. Okay, okay, so let's move to next slide. Next is alphabet. Alphabet is represented by sigma. Okay, the word alphabet is represented by sigma, and alphabet is nothing but non-empty. Okay, see, terms are very, very important in this subject. If you are able to grasp each and every term, then this subject will be very easy for you. Otherwise, you will face lots and lots of difficulty in this subject. So please understand these terms very, very carefully, and note down all the words carefully. So it is non-empty. Hence, that means what? It cannot be empty. So non-empty finite set of symbols. Okay, so first condition is it should be non-empty, and second is finite set of what? Symbols. What is symbol? Symbol I have already told you in the previous slide, that is any character. Okay, so let's take example of alphabet. Say alphabet can be 0, 1. Yes, this is perfect example of alphabet. Sigma can be A. This is perfect example of alphabet. Then sigma can be A, B, C dot 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 up to Z, and capital A, capital B, capital C dot 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 up to Z. Yes, this is perfect example of sigma. Okay, and can I say like this? Sigma can be 1, 2, 3, 4, 3, then 4. Okay, say okay, let's take this only. This is a good example of alphabet. We can take numbers also, 1, 2, 3, 4. Okay, any character we can take now. So in the previous slide we should add all these things also. So do not consider 1 as a number, do not consider 2 as a number, do not consider 3 as a number. All these are characters only. So do not consider 0 as a number. Okay, so up to 9 we can take all these things also. Okay, so 0, 1, 2, 3 up to 9, these are also symbols. So we can take like this also, say 1, 2, 3, 4 and so on, like 0, 1. Okay, so these 0 and 1, these are not numbers, these are just like characters here. Okay, so 1, 2, 3, 4 and so on. So do not say 0, 0, 0, 0 means 0. No, this is not the case here. Okay, so these are characters. Okay, I will come to this point few minutes later. Okay, so if you just leave this point. Okay, just leave this point, but just you should have idea. Actually I have said this point just to give you idea that these are characters and not numbers. Actually you will say 3 times 0 means 0 only as a number, but we won't say here 3 times 0 is equal to 0. So these are not equal. If you are able to grasp this point, then okay. Otherwise I will come to this point few minutes later, don't worry about it. Okay, Okay, so sigma can be this also. Now my next question is, can sigma be like this? Can I have sigma like this? No, sigma cannot be empty. Similarly, can I have sigma like this? Sigma is say 1, 2, 3, 4 dot up to infinity. No, it cannot be up, it cannot go to infinity because it is finite set. Okay, and second is known empty. I hope I have cleared this point. So let's move to next slide. This is alphabet. Okay. Okay. Next is string. String is nothing but finite sequence of symbols from sigma. Okay. Finite sequence of symbols from sigma is string. Okay. So for example, say and please keep these terms in mind. From sigma, you have to take finite sequence of symbols from sigma. If I say string is a b c, this is a string. No, you cannot say this is a string. You first have to specify me what exactly is sigma. If you say sigma is a b, then this string is not a valid string. Why? Because I have used the word finite sequence of symbols from sigma. You have to take symbols from sigma only. Okay, so sigma is ab, then how can I say abc is a string? It is not a string. Okay, so but if I take sigma as a, b and c, okay, then this is a string. Then this is perfect example of string. Similarly, if I take sigma as a b c d, okay, then also this is perfect example of string. No problem in that thing. Okay, so I hope I have cleared this term string. So string means like this. Say let's take one more example, 0 1. Okay, so binary alphabet, this is known as binary alphabet because of two symbols 0 and 1. So I can take string as 0 1 0 1 1 0 1 1 0 1, like this. This is also a string. 1 0 1 1 0 1, this is a string. 1 1 0 0 1 1 0 1, this is a string, and so on. I hope I have cleared this point. Okay, so this is string. Okay, so string, please mind these words: finite sequence. Okay, this is a finite sequence. So I cannot have string of infinite length. Okay, so I cannot have characters, infinite characters in a string. Just like this, you can remember like this. So I cannot say 1 0 1 0 1 1 0 1 dot 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 dot. No, this is not a string. Okay, so always remember, whenever you are writing a string, first specify sigma. Again, if I say this is my string 1 2 3 1 2 1 1 0 1, this is a string. No, I cannot say that. First specify the sigma. If my sigma is say 1 2 3, now this is perfect example. This is a valid string. Okay, but if my sigma is 1 2, then it is not a valid string, because how 3 came here. Okay, I hope I have cleared this point. Okay, now again, very important point. See these things carefully. Sigma is okay. So now I can give you, you can say in the previous slide. Okay, I have said na, 000 is not equal to 0. Now I think you will grasp it properly. 000 is a string, and single zero is also a string. Obviously these two strings are not equal. Okay, now I can say these words also. Okay, similarly, so 000, you won't say that this is a single zero, because zero is a character here. Okay, so here sigma is 0 1, and on sigma 0 1 I am constructing string like this, 000, and another string is 0. So these two strings are not equal. Okay, please remember all these facts. These are very beautiful things and very important things also. I am giving stress on these terms because not today, day after tomorrow, or after few days, you will feel confusion in all these things. Okay, and let me give you one more example. So sigma is say 1 2. Okay, and I have made a string s is equal to say 4 times 2. So I can write this as 2 power 4 also. Okay, this is a shortcut. Similarly, if I write say double 2, I can write it as 2 power 2 also. Okay, and so on. I think you are getting my point. Now let me give you one more basic term. 2 power 4 is 4 times 2. 2 power 2 means 2 times 2. Similarly, 1 power 5 means what? 5 times 1. Okay, now my question is, what is 1 power 0, or what is 2 power 0? 1 power 0 will be what? We cannot say it 1. No, please do not say this is not mathematics. You cannot say 2 power 0 is 1. We are not considering mathematics. And please do not say 2 power 4 is equal to 16. No, this is not mathematics. 2 power 4 means 4 times 2. 2 power 2 is not 4 here. You cannot say it is 4. Okay, we will say 2 power 2 is 2 2 times 2. 1 power 5 is 1. No, according to mathematics, 1 power 5 is 1. But here we will say 5 times 1. Similarly, 1 power 0. What will you say about 1 power 0? What will you say about 2 power 0? So we cannot say it 1. Okay, we will say it as null, like this, or like this, null, lambda. Okay, so different books have different notations. Some books did not like this also. Okay, different books have different notation. So we'll represent 2 power 0, 1 power 0 as this. So null is nothing but null string. Okay, this epsilon is nothing but null string. Null string. Okay, so this term you have to remember. Null string means a string which do not have any symbol. Null string means absence of symbol. Okay, null string means string which do not have any symbol. String which do not have any symbol. Which do not have any symbol. Okay, which do not have any symbol, or you can say absence of symbol means null string. Absence of symbol means null string, means epsilon string. Okay, that means nothing is present in it. So you can visualize it just like free air. It is just like air. Okay, free air. Nothing is present. Nothing means null string. Okay, I hope I have cleared this point. So let me short this thing so that everything come on one slide and you can easily note it down. Okay, so please note it down, all these things. Let's move to next slide. Okay, see, next is length of string. Next definition is length of string. Length of string means number of symbols in the string. Okay, length means number of symbols in string. Okay, for example, say sigma is 0, 1, and I write string like this. So what is length of this string? This is 5. Okay, mind the wording. I have not used number of different symbols. I have used the word symbols. So symbols means count these symbols 1, 2, 3, 4, 5. So length of this string will be 5. Okay, so if I write W as 1, 0, 1, 1, then the length of W will be represented like this. So W here is string. Okay, W is string. So length of W will be 4. Okay, I hope I have cleared this point. So this is known as length of string, that is number of symbols in the string. Okay, let's move to next slide. Next definition is substring. Substring means 0 or more continuous symbols taken from string. Okay, 0 or more continuous symbols. Please mind the word. Each and every word you have to remember. Continuous terms are very important in TOC. I am repeating again and again. These terms are very important in TOC. Okay, and please mind the word continuous symbols, and please mind the word 0 or more. Okay, so let me give you some example. Say sigma is A, B, C, and D. Okay, now if I write string as W as A, B, C, D, so tell me about something. Okay, so first is null, then A, then B, then C, then D, then AB, AC, BC, CD, BCD, ACD, ABD, ABC. I have given few examples. Firstly, tell me all these things, whether these are strings or not. Null is perfect example of substring. Why it is substring? Because I have used the word 0 or more. Okay, 0 or more. So if you are taking 0 symbol itself means null string. Null means free air. I have already told you. You can visualize it like a free air. Okay, so null is free air. So air is everywhere. So you can think like this also. So null is everywhere, or you can say null is substring of every string. Okay, so please remember this word. Null is substring of every string. Null is substring of every string. Substring of every string. Okay, whatever string you take, null will be substring of it. Okay, always remember this thing. This is very, very important point. It will confuse you. Okay, so null is substring. A is obviously a substring. B is substring. C is substring. D is substring. Substring of length 1. All these are substrings of length 1. What about my AB? Yes, AB is a substring. AC is not substring. Why? Because I have used the word continuous impulse. You have to take continuous impulse. BC is a substring. BC is a substring or not? Yes, BC is a substring. Yes, we are taking continuous impulse. CD is also a substring. BCD is again substring. ACD is not substring because we have not taken continuous impulse. ABD is not substring because it is not continuous. ABC is substring. Yes. Okay, I hope I have cleared this point. Substring. Okay, now let's move to next slide. Next slide is language. Okay, what is language? Next term is language. See, language is nothing but set of strings. Okay, so if you take any set of strings, that will become a language. For example, sigma is 0,1. Okay, sigma is 0, 1, and I have taken strings like 101, 110, 1011, 1100. Okay, I have made this as a set of string. This will become my language. Okay, so language is nothing but some set of strings. Okay, so next example, this is L1. L2 can be, say, another language, 1011. This is also a language. No doubt we have taken one string, but it's okay. I can take one string also. We are taking set only. Okay, L3 can be like this also, like this. This is what? This is 5. Empty set. See, language is nothing but set of strings now. So you know what is a set. So if we have taken a set in which we have not even a single element, then that is nothing but empty set. Okay, so this is represented by 5. Okay, so see here, set is what? Collection of something, and here elements, or you can say elements of this set will be in L1. Element of this set is these 4 strings. Okay, so this is first element, this is second element, this is third element, and this is fourth. So we have 4 elements in this set, and this will become a language. Okay, and each element is a string. Similarly, in L2, we have only one element, that is only one string in this language. So that is L2. L3, we have no element in this set. That is, not even a null string is present in this language. Please remember all these things. It will confuse you in few after few slides. You will get confusion about all these things. So please keep all these things in mind. L3 is empty language. Okay, so this language is represented by 5. 5 is nothing but your empty set now. So this is nothing but your 5 is empty set. So empty set means what? It does not have any element. So here also I'm saying this thing only. We have a set in which we do not have any string. Okay, and indirectly we are saying it as empty set. Okay, so I hope I have made this point. So L3 is 5. Okay, so 5 means what? Empty language. 5 means empty language. 5 means empty language. Okay, so empty language means it does not have any string. It does not have any string. It does not have any string. Okay, so this is L3. Now let's move to another language, say L4. So my point here is, can we have only finite languages, or can we have infinite languages also? Obviously, language is nothing but set of strings now, so it is a set only. So can we have a finite set only, or we can have infinite set also? Yes, obviously we can have infinite set also. Similarly, we can have infinite languages also. See, language is nothing but set. So whatever thing you know about sets, that is that will be applicable to languages also. So in a few lectures, after few lectures, we will do union of languages, intersection of languages, complement of languages, and so on. We will do lots and lots of things. Okay, so whatever thing you know about sets, that will be applicable to language. That's it. I can say like this also. So we can have infinite languages also. So give me some example of infinite languages. For example, obviously I cannot write like this now. 101, then 110, then 101, dot. No, this is not the correct way to represent. I think you already know, na, we cannot represent infinite sets in listed form. this is listed form now, so we cannot represent infinite sets in listed form. Similarly, here also we cannot represent languages, infinite languages in listed form. Okay, so we have to use set builder format or statement format and so on. So I can say L4, okay, or you can say L5. Okay, let's take another language, L5. L5 is, okay, all those strings which start with 1. All those strings which starts with 1. Which starts with 1. Okay, so I think you can you can list some strings of this language. Say smallest string will be 1, okay, because it is starting with 1. Second will be double 1, then 1 0, then triple 1, then 1 0 1, then 1 1 0, dot 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 up to infinity. Okay, so all these strings are starting with 1 only. Okay, similarly we can have language ending with 1, starting with 0, ending with 0, starting with double 1, ending with double 1, and so on. There are lots and lots of infinite languages. Okay, I hope I have made this point clear to all of you. So language is nothing but what? Set of strings. Okay, so anything, any set. See, we have already studied about set theory. I hope you have studied about sets. So all these things will be copy pasted here also. Okay, so language is nothing but set of strings. So every concept which you have studied in set will be applicable to languages also. So you can say language is a special set in which each element is a string. Okay, that is the good way to remember these things. So language is a special set in which each element is a string. Okay, I hope I have made this point clear. You can note it down. I have okay, so let me write this thing. Okay, so you should not get confused. Language is special set. Language is a special set in which each element is a string. Okay, so please note it down, this definition. This is also important. Okay, now let's move to next slide. This is summary of all the topics which we have studied till now. First we have studied symbol, then we will jump to alphabet, then we will make string, and then we will make language. Okay, so first basic thing is symbol, that is the building block of the subject. Then from symbols we make alphabet, from alphabet we make string, and collection of string will make language. Okay, I hope I have made this point clear. Let's move to next slide. Now we will do some questions. Okay, so first question is the number of strings, okay, the number of substrings, okay, of length, of all length, number of substrings of all length inclusive that can be formed from a string of length n whose all characters are different is. So these are some options. This question is of GATE 1994. Okay, let's move to next slide and try to solve this question. So first of all, we have to think some example. Okay, after taking some examples, you will definitely get answer of this question. See, let us take sigma as ABC. Okay, now I will take string w as ABC only. Why? Because I have used the word string of length n whose all characters are different. Okay, we cannot repeat any character in the string, so we have taken string w as ABC, or you can take w as AB, or you can take but I am asking a question, can we take w as ABC AB? No, we cannot take like this, because I have used the word here all characters are different. Okay, so all characters must be different, so we cannot take this example. We can take this example, we can take this example. So let's take this example first. Okay, if w is AB, then how many substring will be present for this string? Okay, this is the question. So take lengthwise. Substring of length 0 will be null, substring of length 1 will be A and B, Substring of length 2 will be AB. Okay, so these are total 4 substrings of this string W. Let us take this W ABC. Now, what about you can say strings? So substring of length 0 will be null. Substring of length 1 will be A, B, C, and three strings we have for of length 1. Of length 2, will be A, B, B, C. Okay, and of length 3, A, B, C. Okay, let's take sigma as A, B, C, D. Okay, and take W as A, B, C, D itself. Now let's you can say write all the substrings. Null, then A, B, C, D, then A, B, then B, C, then C, D, then A, B, C, then B, C, D, then A, B, C, D. Okay, so every string is substring of itself. I think you already know all these facts. This is very basic thing. Okay, so every string is substring of itself. So AB is substring of AB. Okay, why I'm saying all these things? Because I have already told you the definition about substring. See the substring: 0 or more continuous symbols taken from the string. 0 or more continuous symbols, 0 or more. So you can take entire string itself also. Okay, so entire string will be substring of itself. And in fact, these are known as trivial substring. Okay, so we have two trivial substring. Trivial means which need not be proved, or which is so obvious, which is very, very obvious. So trivial substring will be null and string itself. Okay, so let me write these things. Trivial substring. Trivial substring. Trivial substring will be null, that is a length 0 string, and string itself. String itself. Okay, so see the question. In the question, they have used the word all length inclusive. All length inclusive. Okay, so we have to consider null and string itself also. If they said, if the question is like how many substrings, yeah, how many non-trivial substrings, then we won't consider null and string itself. Okay, we won't consider null and string itself if they are saying non-trivial substring. Okay, but if they are saying only string, that means all length inclusive and so on, then we have to take null and string itself also. Okay, so let's do it now. How to solve this question? Now let's see this thing. See, substring of, see here, substring of length 1 will be how many? Exactly 2. Okay, and substring of length 1 here are exactly 3. Why 3? Because it has 3 characters. Substring of length substring of length 1, substring of length 1 will be 3 here, because we have exactly 3 characters in the string. Substring of length 1 will be 2 here, because we have only 2 characters here. Substring of length 1 will be here 4, exactly 4. Okay, why 4? Because here we have 4 characters. Okay, so substring of length 1 is nothing but n. If the string is of length n, then substring of length 1 will be n. Okay, so let me write all these things also, so that things become clear and we will be able to save time. Okay, substring of length 0, starting from length 0, substring of length 0 will be only 1, that is null itself. Substring of length 1 will be how many? N. Okay, because string will have n character, the length is n. Okay, substring of length 2, substring of length 2 will be how many? See from this example, ABCD. Substring of length 2 will be what? AB, BC, and CD. Okay, we have only 3. Why only 3? See here, A, B, C, D, E, F, G. Let us take this string. Now length 2, now we are considering length 2, so we are making pairs. Continuous symbols, we have to take continuous symbols. So AB, then BC, then CD, then DE, then EF, then FG. Okay, so all these are 2 length string. So I can say we are making pairs. A will make pair with B, then B will make pair with C will make pair with D will make pair with E will make pair with F will make pair with G. What about G? G cannot make pair because we do not have any extra symbol after G. So one symbol will be left. So directly and indirectly, I will say n minus 1. Okay, so length 2, substring of length 2 will be n minus 1. If string is of length n, then n minus 1 will be number of substrings of length 2, because last symbol will be left unpaired. Similarly, substring of length 3 will be how many? I think you will be able to guess, n minus 2. Why n minus 2? Because see here, say where should I write? Okay, so let me write it here itself. Okay, so let us take this example: A, B, C, D, E, F, G. Okay, length 3 na. A will make pair with BC, B will make pair with CD, C will make pair with DE, D will make pair with EF, E will make pair with FG. What about F and what about G? They won't be able to make pairs. So last two symbols are left. So hence length 3 will be n minus 2. Similarly, length 4 will be n minus 3 dot 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 dot. Okay, so we will come to length n. Okay, so because string is of length n na, so length n substring will be how many? Length n substring will be n minus 1. Please see this carefully. 4 then 3, 3 then 2, 2 then 1. So n then n minus 1. Okay, so n minus 1, that will be equal to 1 here. Okay, so similarly substring of length n minus 1 will be how many? N minus 2. So it will be 2 dot 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 dot. So I hope now you have got the point. So 1 2 3 dot 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 up to n, we have to sum all these things plus 1. So 1 plus 2 plus 3 dot 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 up to n plus 1. So this is sum of n natural number, that is n into n plus 1 by 2 plus 1. So these are the total number of substrings, all length inclusive, of a string which have whose length is n and all characters are different. Okay, so answer to the previous question will be n into n plus 1 by 2 plus 1. Okay, so this is my correct answer. Correct answer is D here. Okay, so let me give you some more idea. Okay, so if the question say, see, if string itself is not included. Okay, string itself not included, string itself not included, then how many substrings will be there? N into n plus 1 by 2. Okay, we will subtract this one because we are not included string itself. Similarly, if we say null string is not included, null string is not included, null string not included. Okay, if we say null string is not included, then again answer will be n into n plus 1 by 2, because we are not including null, so this one will be subtracted. So answer will be again n into n plus 1 by 2. Okay, now if we say trivial substrings are not included, trivial substrings are not included. If question say trivial substrings are not included, then what will be the answer? Trivial substrings are not included. Then what will be the answer? N into n plus 1 by 2 minus 1. Why we have minus 1? Because we are doing plus 1. So this one will be subtracted for, say, we are not included string itself, and we have not included null also. So we have to subtract 1. Okay. So if you want to say in very simple wording, then total number of substrings will be n into n plus 1 by 2 plus 1, and we will subtract minus 2. Minus 2 for what? Null and string itself. So answer will be n into n plus 1 by 2 minus 1. Okay, so this will be my final answer. Okay, so let me put everything on one slide so that you can note it down. Okay, so please note down all these things. Okay, so this is my final answer. So answer will be n into n plus 1 by 2 plus 1. And if string itself is not included, then n into n plus 1 by 2. If null string is not included, then n into n plus 1 by 2. And if trivial substrings are not included, then n into n plus 1 by 2 minus 1. Okay, so I hope I have made the point clear to all of you. Now let's move to next question. Next question is the number of substrings of all length inclusive that can be formed from a string of length n whose all characters are same. Okay, if we take all characters are same, then how many substrings will be there? Okay, so again this is very simple question. Let's first take example. Okay, then we will jump to this question. It says if sigma is say a comma b. Okay, now w will be A like this. Okay, all characters are same. Okay, now we want to find how many substrings. Okay, so again, this is very simple question. W is say 5 times A. Okay, so now substring of length 0 will be what? Again, do like this only. Substring of length 0 will be what? Only one, that is null string itself. Substring of length 1 will be how many? Only one, only one. Okay, so substring of length will be what? 1 will be what? A. You want write all these things because this A and this A, these all are same. Okay, earlier when string was ABC, if we take string as ABC, length 1 strings will be A, B, and C. So we will consider three substrings of length 1, but here we will consider only one substring of length 1. Why? Just because all characters are same. I hope I have made the point clear to all of you. Now length 2 will be only one, that is double A. Length 3 will be only one, that is triple A, and so on. Okay, so length n will be only one, that is string itself. So all these ones will be now added. So answer will be n plus 1. Okay, why n plus 1? Because 1 to n, that is, these all are n, and plus 1 for 0. So answer will be n plus 1. Okay, I hope I have made the point clear. So answer will be n plus 1. Okay, so now next, let's move to next slide. So the question is number of substrings of length n that can be formed using k symbols. Okay, the number of substrings of length n that can be formed using k symbols. Now length is fixed. See, please read the question carefully. Length is fixed, that is n. Say this is n. Okay, length is fixed. Now k symbols we are using. So length of sigma is given to you as k. Okay, so if sigma is say 0, 1, then length of sigma will be 2. Okay, so length of sigma is k here, fixed. So let's take this simple example. So at the first place we have how many options? K options. Say a1, a2 dot 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 up to a k. Okay, so let's take sigma as a1, a2, a3 dot 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 up to a k. So length of this sigma will be k here. Okay, so at first place we have k options, at second place again we have k options. Okay, and third place also k options, fourth place also, fifth place also, dot 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 up to nth place also we have k options. Okay, so final answer will be what? K multiplied by k multiplied by k, k multiplied by k multiplied by k dot 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 up to n times. Okay, so answer will be k power n. Okay, I hope I have made this point clear to all of you. Answer should be k power n. Okay, so please do not try to cram all these things. By hearting is crime for the GATE exam. Do not by heart anything. Okay, so please again try to understand. If you are not able to understand all these things, then please rewind the video and again try to watch all these things. These things are very, very important. And please see the question carefully, understand the question carefully, and only then answer it. Okay, so here we have used the word length n and using k symbols. So answer is k power n. If you by heart this question, that answer is k power n, k power n, then in GATE exam they will use length with k and formed using n symbols. They will say like this. Okay, so then obviously answer will become n power k. Okay, so string is of length k and that can be formed using n different symbols. So a1, a2, a3 up to an, second choice, second place a1, a2, a3 up to an, and so on. So all these so at each and every place we will have n options and total number of places are k. So answer will be n power k. Okay, so please do not cram anything, just try to understand each and everything. Okay, so here we have completed our first chapter of TOC, that is the basic terms used in TOC. Okay, so thank you all of you. We have completed our first chapter successfully in this video itself, and in the next video we will start this chapter, that is finite automata and regular languages. In first few minutes I will discuss the syllabus of this chapter. This is I will say this is a very huge chapter. Okay, this is a huge chapter. Okay, and cover almost 50% of the TOC. Okay, so we will cover this subject, this chapter in pretty much detail. approximately you can imagine 10 lectures for this FA and regular languages chapter only. Okay, so my plan is I will cover this chapter in 10 lectures, then remaining 3 to 4, or you can say approximately 4 lectures for this topic and approximately 6 lectures for this topic. So total lectures will be 20 for this subject, 20 or 21, you can imagine like this. Okay, so in future the next 10 lectures will be of FA and regular languages. Okay, thank you so much. Bye bye.